dual nature of radiation. What is this dual nature of radiation? The radiation can behave as wave. So in various experiments like diffraction experiments, interference experiment, we can see the radiation is acting as a wave, and in some other experiments we can see it is acting as a particle. For example, photoelectric effect, Compton effect, and pair production. So the radiation has two nature. One is wave nature and other is particle nature. And here this radiation is nothing but light. And how this radiation is generated? If a charged particle is oscillating, that is, acceleration is there, deceleration is there, right? So as a result of acceleration and deceleration, a wave will be formed, that is, radiation will be formed. And for this radiation, it has certain wavelength lambda and it has certain frequency nu, and its energy E will be is equal to h nu, where we know nu is c by lambda, that is hc by lambda, that is equal to hc is equal to 12,400 eV by lambda in Armstrongs. So you can find out easily the energy associated with a particular frequency or particular wavelength. And we call the packet of energy h nu as photon. And what is the mass of a photon? The rest mass of a photon is equal to 0. If the photon is in rest, then it doesn't have any mass. And if it is in a motion, then it will have certain mass. And what is that mass and how we can find out? We have two relations. One is Einstein's famous relation E equal to mc square, and we know another energy relation, that is E equal to h nu. So we can equate mc square is equal to h nu. Therefore, we can find out the mass of the photon, that is m is equal to h nu by c square. So the rest mass of photon is 0, and when it is in motion, the mass will be h nu by c square. Noether's theorem. What is Noether's theorem? Noether tells the nature loves symmetry. We also like symmetry, right? The most attractive architectures or something, and all will be have some symmetry. So this is the Noether's theorem, that is, nature loves symmetry. And nature is made up of two things. One is radiation and other is matter. And we know this radiation has a dual nature, that is, it can behave as a wave and also it can behave as a particle. So in interference, diffraction, polarization, etc., the radiation acts as a wave. And in some phenomena like a photoelectric effect, Compton effect, pair production. What is this pair production? A photon can become an electron and a positron. So that is the pair production. So the photon become the particle, right? So the radiation have this symmetry, that is, it have a wave nature and a particle nature. So the matter also should have this behavior. because nature loves the symmetry. So matter also should have a wave behavior and particle behavior. We are familiar with the particle behavior of matter in various experiments like GM counter, and matter behaves as wave in some other experiments like Davison-Germer experiment and G.P. Thomson experiment and Young's double slit experiment of electrons. Okay, so matter also have dual nature, that is, it can behave as particle in some phenomena and it can also behave as a wave. And we will discuss more about the wave nature of matter under this section, the Broglie wavelength. Okay. Dual nature of matter. So from the Noether's theorem, that is, nature loves the symmetry, so matter also should have a dual nature. So it will behave sometimes as particle and sometimes as a wave. And about the wave nature of matter, de Broglie introduced the idea of de Broglie wavelength. What is de Broglie wavelength? If a particle of mass m is moving with certain velocity v, then there will be an associated wave, and the wavelength lambda of this wave will be equal to h by p, where p is the momentum, that is h by mv. This is the famous de Broglie wavelength. Now I am going to discuss about the concept de Broglie wavelength in two different cases. One is non-relativistic case and other is relativistic case. So we will discuss various examples under non-relativistic case and under relativistic case. First one, non-relativistic case. The first example is of a free particle. What is the condition for a free particle? For a free particle, the potential is equal to 0. That is the total energy of the particle, that is E will be equal to kinetic energy plus potential energy. Here the potential energy of free particle is 0, therefore the total energy is kinetic energy, and we know kinetic energy is equal to p square by 2m. So we can find out the p, that is p will be equal to root 2me, and we know the de Broglie relation, that is lambda is equal to h by p. Therefore this will be equal to h by root 2me. So this will be the wavelength corresponds to a free particle. Second example, a bound particle. For a bound particle, its potential energy is not equal to 0. An example of a bound particle case is photoelectric effect. So when a photon is falling on a metallic surface, the bound electron will come to the surface, then it will be ejected from the metal, right? So take the bound particle to the surface, we have to give some energy, that is threshold energy, that is phi. So this threshold energy is the potential energy of the electron, and when it ejected, the remaining energy in the photon will be converted to its kinetic energy. So the total energy E is equal to kinetic energy plus potential energy. Here that is E equal to kinetic energy, we know it is equal to p square by 2m, and here the potential energy is threshold energy, that is phi. So we can find out p square by 2m is equal to E minus phi, that is we can find out p is equal to root of 2m e minus phi. So we can find out the Broglie wavelength lambda, that is h by p, that is equal to h by p is root 2m e minus phi. Third example, a charged particle. Suppose a charged particle is placed in a potential V. Charge Q is placed in a potential V. Then the energy will be kinetic energy, and that will be equal to QV. And we know kinetic energy is equal to P square by 2m, that is equal to QV. So we can find out this P value, that is root 2m QV. Therefore we can find out the corresponding de Broglie wavelength lambda, that is h by p, that is h by root 2m QV. Now we are going to deal about the second case, that is relativistic case. Now we are going to consider the de Broglie wavelength of relativistic particles. What is a relativistic particle? If the kinetic energy of the particle is very much higher than its potential energy, then we call it as a relativistic particle. And here we are going to use the special theory of relativity to find out the de Broglie wavelength. So in the special theory of relativity, you should know one thing. What is special about special theory of relativity? That is, in the special theory of relativity, Einstein taken one consideration that potential field is equal to 0. So the particles is moving in a potential that is equal to 0. That is, there is no potential field is considered in special theory of relativity. But he included this idea of fields in his general theory of relativity. Okay, so what is special about special theory of relativity is potential is equal to 0. And you know from special theory of relativity, if a particle of mass m0 is traveling with a velocity which is approximately equal to c, then its mass will be increased to m, where m is equal to gamma m0, where this gamma is called Lorentz factor, and its value is given, that is gamma equal to 1 by root 1 minus v square by c square. So you can see the mass of the particle when it is moving with a high velocity, its mass is increased by a factor, that is Lorentz factor. See, it is not the weight of the body, it is the mass of the body. That means the fundamental property is changing when the particle is moving with a high velocity. You know, our mass is same even if we are in the earth or moon, but our weight will change if we go to moon or some other planet. But our mass is constant, right? But here you see the fundamental property, that is mass itself is changing with the velocity. And you know the rest mass energy, that is E will be is equal to m0 c square. This is famous Einstein's mass energy relation. So similarly, when it is moving with high velocity, then energy also will increases, that is become gamma E0. So what will be the total energy of this particle? E. That is, you can see it have a rest mass energy and it is moving with certain velocity v, which is approximately equal to c. So it have a rest mass energy, that is E0, plus it have a kinetic energy due to its motion, that is T. So I can rearrange this equation, that is I can find out the kinetic energy, that is T is equal to E minus E0, where we know E is gamma E0. So I can rewrite this as T equal to gamma E0 minus E0, that is T equal to gamma minus 1 E0. So this will be the kinetic energy of the particle when it is moving at a velocity which is approximately equal to c. That is velocity of the light. And we have one more expression for this energy, that is E square equal to P square C square plus E0 square. So from this equation we can find out P square C square, that will be equal to E square minus E0 square. And from this equation we can find out the value of P, that is equal to root of E square minus E0 square by C. So we got the momentum P of the particle. So we can find out the de Broglie wavelength. What is de Broglie wavelength? That is lambda is equal to h by P. That is here lambda equal to h by P is root of E square minus E0 square C. This is the de Broglie wavelength for a relativistic particle. Okay. And I can express the de Broglie wavelength for relativistic case in another way also. What is that? Here I can replace for this time. That is, we already know the energy, total energy is equal to kinetic energy plus rest mass energy. So now I am going to substitute this value here. So I get lambda r is equal to hc by root E square, that is T plus E0 all square minus E0 square, that is equal to hc divided by root of T square plus 2T E0 plus E0 square minus E0 square. So this 2 term will cancels and we get lambda r in another form, that is hc by root of T square plus 2T E0. This one is an example problem. Here in this question, you have to find out the velocity of the particle when its de Broglie wavelength is equal to its Compton wavelength. You have to find out the velocity when lambda de Broglie wavelength is equal to lambda c. I think you know what is Compton wavelength. That is lambda c is equal to h by m0 c. So we have to find out the velocity of the particle when lambda de Broglie is equal to lambda Compton. So where we have to start? We are starting from the equation for the wavelength of the relativistic particle. That is, we know lambda is equal to hc by root E square minus E0 square. And we know what is E is equal to gamma E0. Right. So I can rewrite this equation as lambda is equal to hc by root gamma square E0 square minus E0 square. That is lambda is equal to hc by, here I am taking this E0 outside. So gamma square minus 1. Right. So we know what is E0 value. E0 is the rest mass energy, that is m0 c square. Now I am going to substitute this here, that is lambda is equal to hc by m0 c square root gamma square minus 1. So I can cancel one of the c and remaining I get lambda equal to h by m0 c into 1 by root of gamma square minus 1, where we know this term is nothing but Compton wavelength, that is lambda c. So in the condition is given when lambda is equal to lambda c, that means this entire term should be equal to 1, right? So we get 1 equal to 1 by root of gamma square minus 1. So from this equation we get gamma square minus 1 equal to 1. That is gamma square is equal to 2. And we know what is the value of gamma. That is gamma is equal to 1 by root of 1 minus v square by c square. So we can substitute this value here. So what we get? We get 1 minus v square by c square equal to 2. So we can again rearrange this equation. That is 1 minus v square by c square is equal to 1 by 2. That is, we get v square by c square is equal to 1 by 2. And finally, by rearranging for v, we get this is equal to c by root 2. So this is the answer. Now this one is a previous gate question, and it is a very simple question. So here the question is to find out the momentum of an atom. So an atom is there, and it emits an infrared radiation of wavelength 1500 nanometer. So it will recoil, okay, and that momentum is given PA. And when it emits another frequency, that is lambda is equal to 500 nanometer, then it recoils with another momentum, that is PB. Here you should know one idea, that is momentum is conserved. Okay, that is momentum of emitted photon is equal to the recoil momentum of the atom. So if we know the momentum of photon PA and the PB, then that will be the momentum of atom also. So how we can relate this momentum and wavelength? That is our de Broglie relation. What is it? Lambda is equal to h by p. So here we can find out p is equal to h by lambda. So I can make two equations, that is PA is equal to h by 1500 and PB is equal to h by 500. So what the question? The question is to find out PA by PB, the ratio. That is equal to 500 by 1500. That is equal to 1 by 3. So the relation is 1:3. That is the ratio of PA by PB is 1:3. That is option C. In this question, the given condition is de Broglie wavelength of proton is same as de Broglie wavelength of electron. That is lambda E is equal to lambda of proton. And from de Broglie relation we know lambda is equal to h by p. That is, this is PE, that is equal to h by pp. That is the momentum of the proton. For this condition to be valid, that is lambda E is equal to lambda p, PE must be equal to PP. That is the linear momentum will be same for both the electron and the proton. Now we can exclude option C and D. So the correct answer is one among A or B. Now we have to check the other condition. What is the other condition? That is about relation between their energies and the masses. The energy is kinetic energy, that is E is equal to P square by 2m. That is, I can write P square is equal to 2me. Now I can make two equations from this one. That is, one is for electron. That is Pe square is equal to 2me energy of electron, and another equation for proton. That is Pp square is equal to 2mp EP. And in the first equation itself, we found that Pe is equal to Pp. That is 2me E is equal to 2mp EP. So from this equation you can cancel this 2 and you can find out the relation between EE and the EP. That is equal to mp by me. So the energy and their masses are inversely proportional. So the option A is the correct one, right?